So we just did this sort of simple example, and I apologize that my boxed answer was actually not on the screen, but where we sort of looked at a turntable that's rotating, and we said that the angular velocity was pi in the k-hat direction, radians per second. Okay, now that is something that's sort of easy to wrap your mind around, because you've actually got a rigid body that is just rotating, right? It's this disk, and it's rotating about it. There's clearly an axis it's rotating about. It really makes sense to talk about what the angular velocity is for that. But I want to do a second example of angular velocity where it's not quite so clear how to think about that. And this is an example where I've got, so this is angular velocity example 2. So this is a slightly harder example. And it's a harder example that is really useful for thinking about what angular velocity actually sort of means from a sort of quantities perspective. So I'm going to draw a coordinate system. So here's the x direction, here's the y direction. And I'm going to imagine that I've got some object that's traveling along in a straight line. Okay? It's a baseball, and it's traveling along in a straight line. And I want to ask the question, what's the angular velocity of that object? Does it even have an angular velocity? And this really comes to a key point, which is that the definition of angular velocity depends on what your coordinate system is. All right? Which seems really sort of counterintuitive, because it sort of seems like if I ask what the velocity of this object is, it wouldn't depend on where I chose to put my origin, whereas the angular velocity actually does depend on where I choose to put my origin. I'll note that on the other hand, if I chose to have a coordinate system that was moving, my definition of velocity would depend on my choice of coordinate system. So really there is an analogy here that angular velocity depends on choice of coordinate system. Linear velocity also depends on choice of coordinate system, but it's a little bit more intuitive for some reason. So how do we think about what the angular velocity is for this particular case? Well, one way to think about it is to think about omega, or the magnitude of omega, as being the time rate of change of the angle, right? And that is not a vector. So it's the time rate of change of the angle theta, where theta is theta as defined in a polar coordinate system. So this object clearly has a value of theta, right? That value of theta is changing as time goes on, right? When it's here, the value of theta is greater than pi over 2. By the time the object is over here, the value is less than pi over 2. Asymptotically, the value of theta is actually going to approach 0, right? So the value of the magnitude of omega actually in this case would be negative, because theta is getting smaller. And the direction of omega, if we think about right-hand rule, the rotation or the change in theta is like this. Omega is going into the page. So it will be less than 0 in this case, and it'll be going into the page. Now we certainly could think about how do we actually find omega here if we were to write the position of this vector in Cartesian coordinates, or in polar coordinates, right? We'd say r is r of t times r hat, and we ask the question, what's the velocity? Well, the velocity of the object would simply be r of t times theta dot times theta hat plus r dot times r hat, right? And so here we can actually see that this value, theta dot, right, is the same as what the value of omega is. So you can actually determine what this angular velocity is using some of the ideas that we've used in polar coordinates. Now you'll note that this answer, right, that omega is negative and going into the page, right, would change if I were to be a different observer, right? If I were to consider the same baseball, but now had a coordinate system where the origin was above what the line of the baseball was. All right, so here's my new coordinate system. This is x prime, this is y prime, right? It's just a different coordinate system. I'm looking at the same baseball. Now in this case, theta initially is some positive value, right? And as time goes on, theta gets bigger and bigger and bigger, right? So for this coordinate system, I would actually say that omega is greater than 0. It's coming out of the page. In both cases, and finally, you can actually imagine that in both cases, the value that you have for omega, the magnitude of omega, actually depends on how far the origin is from this particular point. If I think about this case where the baseball is moving along the axis, right, omega is actually 0 because the angle is not changing until it hits the origin, and then there is an instantaneous change in omega, and then omega remains at 0 again. So there's something kind of weird that happens to this situation when the object goes through the origin, and of course that makes some sense with regard to this way of thinking about omega. Really what you're asking is, for an observer sitting at the origin, how do they turn to watch the object move? And in this case, the observer sitting on the origin turns clockwise. In this case, the observer sitting at the origin turns counterclockwise. And in the case where the object is actually moving along the x-axis, the observer is watching the object, is not turning at all, and then has to instantaneously change from looking backwards to looking forward when the object travels to the origin. So there's a little bit of a warning that here around watch out for the origin.